Okay, so now that I've turned on the recording, you can please type your name into the chat so that we'll get a full record for your attendance. As always, anything that you type before I start the recording doesn't get saved. So you need to type it in now so that I can get your record. Okay, so I usually we go right into the homework. So actually, I was a little disappointed that I don't think I got any homework submissions, even over the 3 weeks. So we'll go over those problems, and but before that, I want to go over some of the material that we did last time 3 weeks ago, so that you got it, Jen? Okay, so that we're all on the same page, and then we can go start our new things. Okay, so. Here's what we have. So what we talked about last week, if you want to remember, is these composite functions, right? When we had two functions, one of which is called f of x and the other one is called g of x, and we were able to compose them in order to obtain a new function that we call f of g of x, sometimes written f following g. And sorry, 1 second. Oh, and so what happens is that f and g have play different roles when you do this kind of composition. So it matters which order you compose them in, right? So f of x equals x squared and g of x equals sine of x, as an example. If you do f of g of x, that means you're first applying sine and then applying x squared. So you get sine of x squared. Sorry, 1 second. Was that Plitnik? Oh, okay. Okay, nice. Did they say they could do something? Did they say they could do something? No, okay. Okay. Um, Sorry about that. And so then the other way is g of f of x, where you do f first and then g. So that means you first make it x squared and then you apply sine. So that's sine of x squared. And so we know that sine of x squared, otherwise written as sine squared of x, is not the same function as sine of x squared, right? These are two different functions. It matters which order you do this composition in. Okay? And so then this question that we talked about last time is, how do we compute the derivative of a composite function? So let's say we know the derivatives of the two pieces. We know the derivative of x squared is 2x, and we know that the derivative of sine x is cosine of x, right? So I'll just recall that, right? The derivative of x squared is 2x, and the derivative of sine of x is cosine of x. Oh, please make the screen wider. I don't think I can. I guess I can do this. This is about as wide as I can do it. Um, does that help? Um, I don't know what if it's something on your phone, but this is kind of the same width that it always is. So I haven't changed anything. Okay. So the question is, if we know these derivatives, then if we know these individual derivatives, how do we compute the derivative of the composition? And the answer is we use what's called the chain rule, which is, one of the last derivative rules we're learning. And so roughly, what does the chain rule say? The chain rule says that the derivative of a composite function is the product of the two derivatives of the two individual functions. But the actual statement is a little bit more subtle. So this is the formula of the chain rule that we talked about last time. So if we have two differentiable functions, which we call f and g, and we compose them to get a new function, capital F, which is f of g of x, then first of all, you can take the derivative of capital F. It is differentiable. The limit defining the derivative exists. And what is the formula for it? Well, the derivative is equal to, oh, and this is also a typo here. That should be g prime of x. So you take the derivative of g and you multiply it by the derivative of f, but instead of just taking the derivative of f, you have to plug in g for x in the derivative of f. So the example, which we saw last time, is, let's say that capital F of x is sine of x squared. Well, then the derivative of capital F of x is going to be what? Well, in this case, we have that f of x is equal to sine of x, and g of x is equal to x squared. So what we get is f prime of g of x. So f prime is cosine of x, but instead of just cosine of x, we don't just have x right here, we actually have to plug in g of x, which is x squared. So we get cosine of x squared. And then you have to multiply it by g prime of x. So that will also get multiplied by 2x. Okay, so the derivative of sine of x squared is actually cosine of x squared times 2x. Okay, it's not simply just cosine of x times 2x, right? You have to throw in this x squared over here. Okay, so this was how we did the chain rule in class last time. Okay. Questions about this procedure or about this example? So this example is from last time's notes. Okay. All right. So if this is okay, let's then start with the first homework exercise, which is the same kind of thing. So we want to compute the derivative of 4x minus x squared raised to the 100th power. So now there is a bad way to do this, which we're not going to do. So the bad way is expand out 4x minus x squared to the 100, then take the derivative. Right? This is a bad way because expanding out 4x minus x squared to the 100 is just extremely difficult. So Abraham asked, is there any proof for the formula? We did basically not a full proof, so there is a proof. If you want to see a proof, let me open my copy of the book. Give me a second. So. So you can see a proof if you want to at the end of proof is at the end of section 2.5 of the book. So if you want to read a proof, you can read it there. But what I did in class last time was it wasn't a full proof, but I gave a justification for why the chain rule works. Okay, it's not a fully rigorous proof, but I showed why kind of the derivative of this composite function should be the product of the derivative of one times the derivative of the other. So if you want to see what is basically almost as good as a proof, it's a pretty good justification, is look at last time's notes. Okay. So they're in there. Okay. So you could expand out this example and take the derivative, but that's going to take you forever because expanding out 4x minus x squared to the 100th power is just not easy to do. So to do it the good way instead, you want to do the chain rule. Okay, and since for the most part we're just learning the chain rule, let's set this up carefully and slowly. So we have that if f of x is equal to 4x minus x squared raised to the 100th power, we want to write this as a composition, as f of g of x for some functions f and g. So the question here is, what is, and we know that if we have this, then f prime of x will be equal to, by the chain rule, that's f prime of g of x times g prime of x. Okay? So the question is, what is little f and what is little g in this situation? So what is our function little f of x here, and what's our function little g of x here? So before we even take any derivatives, what if I want to compose them and get this function, what's my f and what's my g? Remember, g is kind of the inside function and f is the outside function. So does anybody want to take a guess? What function here is acting as my f and what function here is acting as my g? Yep. Anybody? Okay, well, let me show you this visually. What's happening is this inside function here this is the g of x. This is what you're doing first, right? How do you evaluate this function? If somebody gives you x, you first do 4x minus x squared, and then you raise that result to the 100th power. So the g of x is what's here on the inside, and then if you take the entire thing here, that's what's your f of g of x. So what is f? It's what you have to do to g of x to get the full thing. So in this case, g of x is 4x minus x squared, and f of x is x to the 100, right? Because this is what you have to do to 4x minus x squared in order to uh, get the final function. You have to raise it to the 100th power. So you're first applying 4x minus x squared, and next you're applying x to the 100. Is that clear? Because you have to understand how things are created as compositions before you can do the chain rule. So is it clear why this is your f and this is your g here? Okay.
Get that over?
Yep, Abraham.
Yeah. So why if the function is just 4x minus x squared,
Hmm.
what would be the value for f of x and what would be the value for g of x?
Well, then that's not a composition. So you wouldn't write it this way, right? So if it was just 4x minus x squared, you could have g of x be 4x minus x squared, and you could have f of x just be x if you wanted to, because f of x is you're not doing anything, you're just doing the identity. But the point is, for something like that, you wouldn't need to write it as a composition because the derivative of 4x minus x squared, you could just take it, right? It's just going to be 4 minus 2x. It's this function which clearly is composed of two steps, which is first doing 4x minus x squared and then raising to the 100th power. So that's why you need to write it as a composition here. 4x minus x squared, there'd just be no reason to do it. Okay? So this is what we have, and so now we can just apply the formula, right? So by chain rule says that f prime of x is going to be what? It's little f prime, so the derivative of x to the 100, which is 100 x to the 99th, but I'm not going to write x here because this f prime has to be applied to g of x. So instead of putting the x here, I have to put g of x. So maybe I'll actually leave myself a little bit of extra space. So it's not 100 times x to the 99, but it's 100 times 4x minus x squared to the 99. And then you have to multiply it by g prime of x. But we know how to take the derivative of 4x minus x squared, because the derivative of 4x is just 4, and the derivative of x squared is just 2x. Okay? So this is the answer for the derivative. It's still not that nice a formula, but at least we were able to come up with it quickly. It's 100 times 4x minus x squared raised to the 99th power, and all that times 4 minus 2x. Okay? And so this is how the chain rule works. You basically take the derivative as if the inside function didn't exist, and then you just plug the inside function in again, right? So it's 4x minus x squared to the 100. You just bring down the 100 and replace it with a 99, just like you were doing a power rule. But then you have to remember, there's actually something inside here. And that something inside there shows up twice. First, it shows up because you have to just punch it in right here. And second, it shows up because you also have to take its derivative to get a second term over here. Okay, so this is why 99? Because this is when we take the derivative of x to the 100, right? I'll take this as an aside, right? The derivative of x to the 100 is equal to 100x to the 99. This is the power rule, right? So you always decrease the exponent by 1 when you bring it down. So when you're taking f prime here, it's going to be 100x to the 99, but since you're punching in g of x, it's 100 4x minus x squared to the 99. Is that okay?
So that the others,
Yes.
for instance, so I'm now going to distribute the 100 by whatsoever that is in the parentheses there, right?
Yeah, you can't do that because what's in the parentheses here is being raised to the 99th power. So you can't just put in the 100 here. You should think of there as being, an extra parentheses here. It's the same thing, right? So you
Okay.
can't put in the 100. You could, but you'd have to, if you wanted to distribute it, you'd have to take its 99th root, which is maybe not really any simplification. So there's no reason to do it.
Okay.
If you wanted to, you could distribute the 100 with the 4 minus 2x, right? So if you wanted to, you could say that this is the same thing as 4x minus x squared to the 99 times 400 minus 200x. That would be okay because the 100 can get distributed into this last term, but it can't get distributed into this term because there is a 99th power there.
Okay.
Okay,
Thank you.
you're welcome. Other questions? Okay. All right. If no questions, let's do the second homework exercise. So this is a modeling problem. So a model for the length of daylight in hours in Philadelphia, Pennsylvania on the teeth day of the year is given by L of t equals 12 plus 2.8 times sine of 2 pi over 365 times t minus 80. Okay, so it's a complicated function. Okay? So we want to compute the rate of change of the number of daylight hours per day on March 21st and May 21st. So basically, how many more hours of daylight are we getting each day? So in my kind of rough mental calculation, being familiar with Philadelphia since I lived there for 5 years, in March, each day you get about another 2 minutes of daylight. 1 to 2 minutes of daylight each successive day in March. And in May, it's somewhat less than that. It's less than 1 minute of daylight. This is what I think. So let's see if this is verified by this function. So the keyword here is it's asking for rate of change. And rate of change always means derivative, right? Rate of change means derivative when you're doing calculus. Okay. So what we have to do is we have to calculate L prime of t. Okay, we've got to calculate this derivative, and then we're going to need to punch in the correct values of t for March 21st and May 21st, which let me actually just look that up. So March 21st is what day of the year? Let's assume it's not a leap year. So this is going to be actually March 21st is going to be t equals 80. It's the 80th day of the year. And May 21st is t equals 141. Okay, so it's the 141st day of the year. Okay, so let's calculate L of t. Well, okay, you have this 12, right? That's not going to do anything. That's just going to disappear. That's going to be 0. And then you have 2.8 times sine of stuff, right? So maybe actually I'll rewrite this. I'm going to rewrite this because it'll be a little bit easier. So I'm just going to write L of t equals 12 plus 2.8 times sine of, and I'll write this as 2 pi over 365t minus, I'll just distribute it, so minus the 80. So 160 pi over 365. Okay. So then L prime of t, well, this 12 is just going to go, this L prime of t, this 12 is just going to go to 0, right? And now the rest of this here, this 2.8, is just going to stay as a 2.8. And now we're going to have to take the derivative of what's left. So it's 2.8 times the derivative of sine of 2 pi over 365t minus 160 pi over 365. Okay. And this is plus. Okay, so I didn't really do anything here. I just said the 12 is going to become 0. The 2.8 is just going to stay along for the ride because it's a constant. when we multiply by a constant, that constant stays. And then we have d dt of whatever is left. We have to take the derivative of what's left. And now here's where we have to use the chain rule, right? In this chain rule here, this thing on the inside is our g of x, and this sign on the outside is f of x, or g of t, and f of t. In this case, our letter is t because it's representing time. Okay. So what do we get here? Well, this is going to be equal to 2.8 times, now let's, 12 is becoming 0 because we're taking the derivative, right? So any constant, the derivative of any constant is 0. So when we're just adding a constant, that doesn't affect the derivative at all. So this is because we're applying the derivative here. We're doing d dt. This constant stays the same because it's being multiplied by something. So when you have like the derivative of 3 times x to the fifth is 3 times the derivative of x to the fifth. So when a constant is a factor, it always stays the same when you're taking the derivative. When a constant is just a term on its own, it gets killed when you take the derivative. It always goes to 0. Okay. Does that make sense? Okay. So we get 2.8 times. Now we need the chain rule formula again, which I'll recall, right? The derivative is f prime of g of t times g prime of t. This is the chain rule formula. Okay. So the derivative of sine is cosine. So we're going to get cosine of 2 pi over 365t minus 160 pi over 365. And then times g prime of t. Well, this g is just a linear function, right? I mean, it's got complicated constants, but it's just something times t minus something else. So when you take the derivative, this term disappears, and over here, all that you get is the 2 pi over 365, right? So this is times 2 pi divided by 365. Okay, so this is the derivative. Is 2.8 times cosine of 2 pi over 365t minus 160 pi over 365 times 2 pi over 365. Okay, so it's a bit of a complicated looking function, but really all that's going on here is you're using the chain rule for the sign, and you're using standard rules of differentiation for everything else. Constants go to 0, and constant multiples stay along for the ride. Right, so this is how we do the derivative, right? This cosine here, right? This is f prime, and this stuff in here is g of t, right? That's why this rule is working, and this over here is g prime of t. Okay. Okay, so let's punch in values now. I'm going to punch in t equals 80. That gives us that L prime of 80 equals, and then we have t equals 141. L prime of 141 equals, now of course for this I need a calculator, so I'm just gonna go do that now. So we have 2.8 times cosine of 2 pi divided by 365 times 80, and then minus 160, minus 160 pi divided by 365. 160 times, let me do this. Okay, 160, 2 pi divided by 365 times 180 minus 160 pi divided by 365. And then, oh, I see. Oh, yeah, so that's actually going to be exactly that. And then we'll multiply the entire thing times 2 times pi divided by 365. Okay, so the result that we get over here, this turns out to be about 0.048. And if I do the same thing with 141 instead, I get 0.024. Okay, so it's about half. Okay. Oh, sorry, just call me. Yes, Rosh, question?
Yeah, yeah,
Yes.
yeah. Just coming, my internet little bit, giving me tough time, so I just change location.
Okay.
So I just come here, a little bit want to know from the starting point. I don't know if you can help me, please.
Sure. I mean, yeah, I can't review everything, but basically we're just going over the homework from last time, and
Okay,
we're going over this example, which is based on the chain rule. So we have
okay,
to
okay,
compute the derivative of this complicated looking function. And when we compute that derivative, we end up getting this formula over here. And now we're punching in the days. So March 21st corresponds to t equals 80 because it's the 80th day of the year. And May 21st corresponds to t equals 141 because it's the 141st day of the year. And so when we punch in those numbers, we get 0.048 and 0.024. And now what does that mean in terms of hours? Right? I mean, so these are all this so this is the rate of change of in terms of hours per day, right? So I could write this as hours per day and hours per day. Maybe if we convert it into minutes, into minutes, let me actually just write it up here. Sorry that we're running out of space. So March 21st and May 21st, if I can convert it into minutes by multiplying it by 60, I'm going to get that this is so 0.48, so times 60 is 24, and then 28. So this is going to be 2.88 minutes per day. So that's how much longer each day is getting. And on May 21st, it's going to be 1.44 minutes per day. Okay. And so that means that the number of daylight hours is increasing faster in March than it is in May, which makes sense. Exactly, James. And that makes sense because March is near the equinox, right? The days are getting longer faster. May is closer to the solstice. So they stay, the days don't change length as quickly. And of course, if this was done in Monrovia instead of in Philadelphia, you would get a very different function here. And you would probably get, I mean, the day length in Monrovia is much more constant than it is in Philadelphia. So whatever the correct function is here for Monrovia, we would actually get some much smaller, some much smaller parameter here, and you'd probably get much smaller rates of change as well. But I don't know what the exact correct thing is for Monrovia. It probably is basically just changing this 2.8 to something else. And it's some number that's smaller than 2.8. But when we did the trigonometry unit, we did an example where we kind of figured out that function. So if you have your notes from last year, we worked this out in Monrovia and in Ganta. Okay. All right. Any questions? Questions? Okay, great. So that's that example. Okay, so it's increasing faster in March than in May. In March, it's a rate of 2.88 minutes per day. In May, it's 1.44 minutes today. The way that we got those numbers was just by punching in 80 and 141 for t in this expression. Okay. Okay. All right. So what was this application of the chain rule that we talked about last time? So we talked about something called related rates. So it's been a while, so we'll go over this again. So one way of thinking about the chain rule is that if I just give g of t a name, if I just call it u, and if f is a function of u, then f in this case is going to be like f of u, which is really, f of g of t. Then the idea is that the derivative of f with respect to t is the derivative of f with respect to u. That's exactly, other way you can write this is, this is exactly f prime of u, and then times du dt, this is exactly g prime of t. So this is some other way of writing the chain rule. If it's confusing to you, don't worry about it. But the point is that if you have a relation between quantities that vary with time, what this lets you do is if you want to understand how to differentiate this with respect to time, you can differentiate each part as usual. That's the df/du part. And then you multiply it by the derivative of that variable with respect to time. So for instance, an example of this, do the one on the homework. Let's say that you have, a circle is growing. And how does the rate of change of the radius correspond to the rate of change of the area? So how does the rate of change of the radius correspond to the rate of change of the area? Well, the idea is we first write down the formula relating radius to area. So the area is pi times r squared. And then you apply d dt. You apply the derivative with respect to time to find rate of change. So the derivative of a with respect to t is just dA dt. And then the derivative of pi r squared with respect to t is you just take the derivative with respect to r like normal. So this just becomes 2 pi r, and then you multiply it by the derivative of r with respect to t. So this is times dr dt. Okay? So this is the formula that relates the rate of change of the radius to the rate of change of area. So if the radius is increasing at a certain speed, the area is increasing at 2 pi r times that speed. Okay, so this is what we had. So this follows from this formulation of the chain rule, although if you confuses you, then don't worry about thinking about it that much. The point is just that you have these mechanics that, some quantities are related by an equation, and you can take the derivative of both sides of the equation with respect to t. And when you do that, every time you have a term involving a variable, you just take the derivative normally. So pi r squared becomes 2 pi r. And then every time you take the derivative normally, you also multiply by d of that variable dt. So you also multiply by dr dt in order to make that work. Okay? So this is how you can relate the rate of change of area with the rate of change of radius. And so we saw a couple of these related rates types problems last time. Okay? And so let's work through this example that's on the homework where we needed to draw a diagram. So here a plane is flying horizontally at an altitude of 1 mile and a speed at 500 miles per hour, and it passes directly over a radar station. So find the rate at which the distance from the plane to the station is increasing when the plane is 2 miles away from the station. So of course, to even start this problem, we have to draw a diagram. Right? So here's our radar tower. Okay, and now the plane is going this way. And we want to know what is the distance from the plane to the station? How is it increasing when the plane is 2 miles away from the station? So this plane is flying at an altitude of 1 mile. That's the altitude. And we want to look at the plane over here. It's still flying this way when this distance here is 2 miles, right? So we have 2 miles. We have a right triangle here with 1 mile. And we have some, maybe I'm not going to call this 2. I'm just going to call this x. This is kind of what we want to calculate. This is our distance, okay? And then we have some other quantity here, which I'll call y. Okay? I'm making these both variables because these change with each other, right? X is varying, and y is also varying. This 1 over here stays the same. So, right, this is kind of step 0, draw diagram. Step 1 was write an equation relating the quantities. Okay, so Mike, we have a right triangle, right? So the equation relating the quantities is just Pythagoras' equation. So 1 squared plus y squared equals x squared. So step 2 in a related rates problem is differentiate with respect to t, always with respect to t for time, because we're talking about rates. So the 1 squared, that's just 1. That just becomes 0. The y squared, remember how we do these differentiations. Y squared, we take the derivative like normal, so that would become 2y. But since we differentiated a y term, we have to multiply by dy dt. So this becomes 2y dy dt equals, and then on the other side, it's the same thing, but with x instead of y. So equals 2x dx dt. Or we can simplify this, y dy dt equals x equals x dx dt. And what is it that we want to find out? Well, the question is asking what is the rate that the distance from the plane to the station is increasing, right? So this x over here, this is the distance from the plane to the station. Okay? So dx dt, that's the rate of change that we want to solve for. This is what we want. Okay? So in order to do that, we're going to have to solve this equation. We're going to need values for all of the other quantities so that we can solve for dx dt. So the third step is punch in values for the other quantities.
Yeah, I have a
Yes?
question, sir.
Yes, Princeton.
Prince.
Oh, Prince, you're in.
Yeah,
You're in. Okay, yes.
yeah, I'm a little bit confused with after the derivative of y square and x square, we have 2y dy or dt. Okay, here then where we have the y dy or dt equal to x x or dt. How can the two remove from here? And we
Oh,
are not
because
seeing
there's
the
a
two
2.
right
This is an equation, right? There's a 2 on both sides of the equation, so we can cancel it out.
now. Okay, thank you. Thank
Right,
you.
just because it's an equation. Yeah.
All right.
Okay. So now we'll punch in the values for the other quantities. So what are they? Well, dy dt, okay, so x we know. X is equal to 2. That's given, right? That's the distance from the plane to the station. It's 2 at the time, right? The plane is 2 miles away from the station. Dy dt we know because dy dt is just the speed of the plane, right? Y is how far away the plane is in this along a horizontal line from the radar tower. And so if y is its position, we know that the derivative is its velocity. That's its speed. So dy dt is just the speed, and that's given to us. So that's going to be 500 miles an hour. And now what about y? Well, for this, we need to use this equation over here. We know that 1 squared plus y squared equals x squared. So 1 squared plus y squared equals x squared, but x is equal to 2, so that's 2 squared. And if we solve this, this gives us that y squared is equal to 3, and y equals square root of 3. Okay, so this is our value for y. It's square root of 3. And now we can solve the equation. We have square root of 3 times 500, right? Because this is y, and this is dy dt. It's the derivative. Equals, well, x is 2. That's x times dx dt. And dx dt is what we want to solve for. We want to know how fast is this plane moving away from the radar tower. That's going to be an important calculation for, air traffic control. You want to know how far the plane is from your tower. And so doing this, we solve that dx dt, we just divide by 2, is equal to 250 times square root of 3 miles. Okay. It's 250 over square root times square root of 3 miles, and that's about 1.7. So That's about 410 miles or so. Okay, so a mile, I'll say miles per hour. Okay, so even though the plane's flying at 500 miles an hour, the distance from the radar tower is only changing at about 400 miles per hour. And that's because that distance is not, measured in a straight line. That plane is not flying in a straight line away from the radar tower like this, but it's flying in this direction, right? So that's not, it's a part of that. The plane's velocity is not going straight away from the radar tower. There's a part that's just going in this direction. So that means the distance between the plane and the radar tower is actually going to be a little less. Sorry, the speed at which the plane goes away from the radar tower is not quite going to be 500 miles an hour. It's going to be something a little less. In this case, it's about 400 miles an hour. Okay, so these are our steps for any related rates problem. You draw a diagram if that's applicable, label and use variables for anything that changes in your diagram. You write an equation relating the quantities in your diagram. That will usually come from geometry. Then you take that equation and you take the derivative with respect to t. In this case, this leaves y dy dt equals x dx dt. And then you solve for the quantity you want, and by punching in values for all the other quantities. Okay, so James has a comment. When the plane is 2 miles away from the station, the rate at which the distance is increasing is still the plane speed, which is 500 miles an hour. So this is not quite right. This is the paradox, right? The horizontal distance is increasing at 500 miles an hour, but the plane is flying 1 mile above the station, 1 mile above the radar tower. Okay? And so when the plane is flying 1 mile above the radar tower, it turns out that if you take the snapshot now and you take your new snapshot an hour later when the plane's 500 miles away, that the distance from the radar station will actually have increased a little bit less than 500 miles an hour. A little bit less than 500 miles. Okay? I mean, think of it over here, right? I mean, this distance is square root of 3 when we start. But the plane started out 1 mile from the station, and now it's only 2 miles from the station, even though it's traveled square root of 3 miles, which is more than 1 mile. Okay, so that's exactly what makes this a little paradoxical. It can be flying away, but its distance from the station isn't actually increasing as fast as its speed. Okay, and that's why you get this answer that's a little bit less than 500 miles an hour. Okay. Recopy this here, dy dt. Okay, so this is our related rates question. Okay, and we did a few more in the notes from last time. So if you want to review some more related rates, you can always look in the textbook. These related rates questions are in chapter 2.7. So this is all, maybe I'll put this back here. This is all chapter 2.7 in the book. Or if you want to look at some of the notes from last time, we did several related rates problems last time.
Hello?
Hello, yeah, Rush?
Yeah, I have a question. I don't know how to get the 250, the root of 3 miles per hour.
Oh, here, well, we're just solving this equation, right? So we're solving for dx dt, so I'm just dividing by 2 on both sides. Right, this is 2 dx dt equals 500 times root 3. So dx dt, I just divide by 2, so it's 250 times root 3. Is that okay?
So, okay, yeah, I understand.
Okay.
I understand.
Great. Other questions? Okay, great. Okay, so let's move on to new things. Okay, so this we're actually do 3 kind of new topics today, but they're all short. So they're nice. They're nice topics. So this is linear tangent line approximation. So if you want a reference in the book, this is section 2.8 in the book. So let's say we didn't have a calculator and we wanted to approximate the square root of 101. Well, how might we do this? Well, one thing that I could do is I could try to draw the graph of y equals x to the 1/2, right? And know that, square root of 101 is equal to 101 to the 1/2, right? So if I draw the graph of y equals x to the 1/2, it looks something like this. Okay? This is y equals x to the 1/2. And really, what I want to know is, let's say I have my point 101 here and I have my point 100 here. This is not due to scale. I want to know what's the y value when I punch in 101. That would be the square root of 101. But I don't know the square root of 101. But I do know the square root of 100, right? I know that the square root of 100 is equal to 10, right? So I know that if I punch in 100 over here, the corresponding y value is going to be 10, right? So what's the idea? So this is called a linear approximation or a tangent line approximation. The idea is that the tangent line is a good approximation to a graph near a point. So if I'm here at 100 and I draw the tangent line, let me imagine that's the tangent line. It's a bad drawing, but imagine that's the tangent line. Then whatever the y value is here at the tangent line at 101 is going to be pretty close to the actual value at 101. This error is not going to be very big. Okay? So it should be, so basically to get a good approximation, what we want to do is get an equation for the tangent line. And we know how to get an equation for the tangent line because we know that the slope is the derivative, and we know that it passes through a point that we know, right? We know this point 100, 10 is a point that this graph passes through. Okay. So let me okay. So let me redraw this. I'm going to do another page. No, that's not what I want. Page. Okay. So let me redraw this. Just let me just talk about this in general. Right? If I just have some graph y equals f of x, and I pick some point A over here, and I draw the tangent line at A, maybe I'll draw it in red. Let me draw this in red. If I draw the tangent line to the graph at A, then we know that the slope of the tangent line is f prime of A. That's what the derivative is. And so the equation of the tangent line, well, we can write this in point slope form, right? If this is A, then the y value here is f of A. And so we get y minus f of A is equal to f prime of A times x minus A, or we can isolate y. Y is going to be, I'll write it as f of A plus f prime of A times x minus A, right? That's the equation of a tangent line. And now we can just try to punch in a value of x, and that won't give us exactly the value of f of x, but it'll give us the y value of the tangent line at that same point, which should be pretty close, as long as I pick an x that's pretty close to A. Okay? So this is what the equation of the tangent line is going to be. So I'm going to go to this next slide where this is written. So suppose f of x is differentiable at A. The tangent line to the graph of y equals f of x has this equation. This is just copying down what we've written before. And that means for values of A that are near x, this is a good approximation to f of x. So we have this approximation, which is called the tangent line approximation, that in general, f of x is pretty close to f of A plus f prime of A times x minus A. Okay, so what I want to do is let's apply this to finding the square root of 101. So in this case, f of x is equal to, square root of x, or x to the 1/2. A is our guess, or A is the kind of known value. So in this case, A is going to be 100. It's a value that we can punch into the function and we know what the answer is. So we know 100 to the 1/2 is equal to 10. So in this case, f of A is going to be the square root of A, which is 10. And then we want to know what's going to happen at 101. So x is going to be 101 here. Maybe I'll just finish this up over here. No, I'm gonna do this on a separate sheet. Okay, let me recopy this on another page. Okay, so the tangent line approximation says that f of x is close to f of a plus f prime of a times x minus a. This is the tangent line. So in our situation, f of x is equal to square root of x. A equals 100. F of a equals 10. X equals 101. This is what we're trying to approximate. And then what is f prime? Well, f prime of x, well, this is d dx of x to the 1/2. And we know by the power rule, this is 1/2 times x to the minus 1/2. Right? Or another way of writing this is 1/2 times 1 over x to the 1/2, or 1 over square root of x, or another way of writing that is 1 over 2 times the square root of x. Okay, so let's punch everything in. What do we get? We get that the square root of 101 is approximately equal to, well, 10. That's the square root of 100. 10 plus, well, f prime evaluated at 100. So a is 100, f prime of x is 1 over 2 square root of x. So that's 1 over 2 times square root of 100, and then times 101 minus 100. Okay, I'm going to label every term here, right? This is f of a, this is f prime of a, and this is x, and this is a. So tangent line approximation is we know the value of f at a, we want to learn what's the value of f at some nearby point x. And so what happens when we evaluate this? This is 10 plus 1 over 20 times 1, or in other words, this is 10.05. Okay? So this is our approximation. What's the actual answer? The actual answer is that the square root of 101 is, let me put it in on the calculator. So the square root of 101 is actually 10.049876 ... So this is a pretty good approximation, right? Okay, best of luck to your dad, James. So this is a pretty good approximation, right? I mean, if I used a calculator, I get the square root of 101 is 10.0498, some change. Whereas here, without using a calculator at all, just by using calculus and some reasoning and doing an easy computation here, you get that the square root of 101 is about 10.05. Okay? So what you see is you can get a very, very good approximation with no calculator at all. And without calculus, it would be very hard. If I asked you what's the square root of 101, you might know it's a little bit more than 10, but it would probably be pretty hard to, come up with anything very specific. But this tangent line approximation actually lets you get a pretty good approximation to 2 decimal places. This is correct to 2 decimal places. It's even correct to 3 decimal places. Or no, so it's correct to 2 decimal places. So, right, so this tangent line approximation is pretty impressive. Okay, at least when you know the real value at some point close to where you want to learn the value.
Hello?
Yes. Rush? Yeah.
All right. In case you use this method too by saying like this, you look for a perfect square number within 100 by saying
Mm-hmm.
the perfect square root within 100 will understand in 101 is we understand that inside is 100,
Mm-hmm.
and remainder by saying plus the remainder which is 1 or
Mm-hmm.
divided by the square root of the 100.
Yeah.
It still
Right. I
makes
mean,
sense.
that's exactly what comes from this. That's this expression right here. Right? X is the 100, X is the 101, A is the 100, and this f prime of A is the derivative of square root of X, which you can evaluate using the power rule. That gives you 1 over 2 times the square root of X.
So that's mental too. It's not bad, right? When you're asking for
Yeah, I mean, it's just
so
an approximation, right?
what I mean, if you use that mental to what I mean, what I just asking by saying to determine the approximation for that particular expression,
Mm-hmm.
we first thing look within the number. For example, the actual the square root of 5 to look what will be the approximate value. We
Right.
understand that within in the square root of 5, we understand there is a perfect square root within 5. We understand the perfect square root within 5 is 4.
Mm-hmm.
We will
Yeah.
with the remainder will be 1.
Mm-hmm.
We hold constant. We then the next thing we take the first square root is twice of the first square root by saying 2, which have the first square root is 2 plus 2, you get 1 over 4. When we
Mm-hmm.
put in, we get 2.25, right? Something like that,
Perfect.
right?
Yeah. Yeah, so let me write this down just so everybody can follow. So Rash is just doing another example, square root of 5 by same method. Right? In this case, we would have 4 is the closest value. So square root of 4 is the closest value we know. And we would again get that the square root of 5 is approximately equal to, well, over here we would have the square root of 4 plus 1 over 2 times the square root of 4 times 5 minus 4. It would be the exact same thing. This would be, f of A, this would be f prime of A, and this is our x, and this is A. And right, so when you evaluate this all, this becomes 2 plus 1/4 times 1, which is 2.25. And the actual answer is pretty close. Actual answer is not quite as close, but it's still pretty close. The actual answer is square root of 5 is about 2.236, and so on. Okay, so it's not quite as good as for 101, but it's still pretty good. You're getting a decimal place at least, and your second decimal place is not off by that much. It's 2.25 versus 2.24. Yeah, so you get a pretty good approximation here. Yeah, so you can use this for square root of any number, and the closer your number is to a perfect square, the better an approximation you'll get. So you could try to approximate, the square root of 65 or something like that. You'll get a better approximation than you do for square root of 5, for instance. But if you try to do something like square root of 90, then maybe your approximation won't be quite as good, because 90 is a bit far from perfect squares. It's far from 81, and it's far from 100. Okay, any further questions on this? Let me just go back to the slide here. So this is our general formula for tangent approximation. So this works anytime you've got a differentiable function and you want to evaluate it at some value x, but you don't know the value. You only know the value at some nearby value a. So like if square root, we know square root of 100, we don't know square root of 101. The a here is going to be the known value, and the x here is going to be the unknown value. Okay, that's how this works. And let me do this in a particular example. Let's imagine you want to evaluate sine of a very small angle. So this is something that happens in physics when you're trying to describe the motion of a pendulum. for instance. So let's apply this with f of x equals sine x and a equals 0. Well, what do we get here? We get that sine of x is approximately equal to, well, sine of 0, right? That's this f of a, plus, well, f prime is cosine, so plus cosine of 0 times x minus 0, right? This here is my f of a. This is f prime of a, and this is x, and this is a, and this is f of x, right? This is what happens with the formula. But if I simplify this, sine of 0 is just 0. So Enoch, I'll show it in a second after I finish this. Sine of 0 is just 0, and cosine of 0 is just 1. So this all simplifies to 0 plus 1 times x minus 0, which is just x. And so what this tells us is that for very small values of x, that sine of x is approximately equal to x. Okay? And a lot of times, so when you're studying certain physics differential equations, that involve very small perturbations, like a pendulum that has a small swing. It turns out that the actual equation would involve sine x, but that makes it too hard to solve. And what this tells you is you can replace this sine x just with x. And as long as x is very small, that sine x is very close to x. And that gives you an equation that you can actually solve. And this is actually where the equation for the motion of a pendulum comes from. Okay, so I'm not going to go and derive all the physics, but if you're interested in it, know that when you're trying to derive the equation of a pendulum, it relies on this approximation that sine of x is very close to x. And this is given by a tangent line approximation. Okay. Yeah, no, Enoch, I saw your comment. I'm going to do it.
The previous page for the square root of 5.
Yes. I'm going to go to that. I just wanted to finish this first. Okay. So now I'll go back to the page for the square root of 5. Yes.
Square root of 5 is what? Oh, okay. Okay.
That's okay? Okay, good. Okay, so these tangent line approximations often give you a way to simplify computations. Okay, you can get, and it comes at the cost that you don't get an exact answer. But what you hope is that your answer is good enough. You get a good enough approximation. Okay? So this is kind of a crude way of doing these approximations. There's a better way called Newton's method, which we're going to talk about next. But before we talk about that, any questions about these tangent line approximations? How we do this? Let me just skip ahead just to show you that, on the homework, there's going to be, can you approximate this 1 divided by 4.002 without using a calculator? Right? I mean, of course, you can just do 1 divided by 4.002 in a calculator, but the idea here is what for your tangent line, so I'll just give you your hint, is that you know that 1 over 4 is equal to 0.25. So what you want to do is use a tangent line approximation for f of x equals 1 over x with x equals 4.002 and a is the closest value that you know, that's going to be 4. So if you use the tangent line approximation formula with f of x equals 1 over x equals 4.002, and a equals 4, then you'll be able to get a good approximation for 1 over 4.002 without having to use a calculator or anything like that. And in this case, your approximation is going to be really good. It's going to be good to like 5 decimal places. Okay, so you can do that completely by hand. You can make this calculation to 5 decimal places without having to do long division or any horrible thing like that. Okay, so this is just a hint for what's going to be one of the homework exercises that also uses these tangent line approximations. Okay, so tangent line approximations are great, but there's an even better thing called Newton's method, which is what I want to spend most of the rest of the day talking about. If we don't get to L'Hopital's rule, we'll do it next time. So Newton's method, let me get the reference for this. Newton's method should be, is this also in 2.8? No, this is going to be in 3.6. So this is section 3.6, if you want to look it up. Okay, so let's say that you want to solve an equation. You want to solve f of x equals 0, and f of x is some differentiable function. So let me graph this equation. Let's say that the equation looks kind of like this. Okay? Let's say this is the graph. This is y equals f of x. And so we want to find this root here. This is where f of x equals 0. This is the root. So now, let's say that I can't find that, but I do know some value that's kind of close to a solution. Maybe I'll call it here. I'm going to call this x0. Well, what's a geometric way that I could try to get closer to a solution? Well, I can do the following. I could draw a vertical line up to the graph, and now I could draw the tangent line to the graph. And where does that tangent line get me? Well, it gets me a little bit closer to the solution, right? So maybe this new point that I'll get here is going to be called, I'll call it x1. I'm sorry, I want to draw that in green. So this is going to be called x1. You know what? Let me, no, this is okay. Okay, this is x1. And now, what do I want to do again? Well, again, I can go up from x1 to the graph, and then I can draw the tangent line to the graph there. Let me put this in a new color. I'll put it in purple. So I can draw the tangent line to the graph again. Right? And this should give me some even closer point, which I'm going to call x2. And the method is that if you keep repeating this, and your initial guess is good enough, if you keep repeating this and your initial guess is good enough, you will converge to a solution to f of x equals 0. Okay? So you kind of like start with a point, draw the tangent line, see where that intersects the x-axis, and then draw the tangent line at that x value, see where that intersects the x-axis, and then keep on going. And as long as you picked a good enough guess, then you're going to end up converging to a solution to f of x equals 0. So this is kind of like the graphical way of seeing this. Okay, and I think this diagram's unfortunately not so good, but the idea is from this x2, you go back up to the graph, draw the tangent line again, and as you get closer and closer, you're getting closer and closer to the root. So you can get it to however many steps you want to do, you can get as many decimal places as you need. Okay. Okay, so this is the concept. So how does the actual mathematics work? Well, okay, I'm going to write this on a new page. So how do we do the mathematics or sort of the formulas? Well, I'm going to draw this again. Let's say that we have some graph over here. Let's say this is my point x0, and this is y equals f of x. And I go up here, and now I'm going to draw the tangent line. In green, I'll draw the tangent line like this. And this is going to be my x1. And so the question is, what is this point x1? All right. Well, we know that this point over here is, this is f of x0. And we know that the equation of the tangent line, we've seen this already, is y minus f of x0 equals f prime of x0 times x minus x0, right? This is the equation of the tangent line, right? This is in point slope form, right? Because we have a point which is x0 comma f of x0. And we have the slope, which is f prime of x0. So this is the equation of the tangent line. And so what's my x1? My x1 is where the tangent line crosses the x-axis. So to find x1, I have to set y equals 0. So x1 given by setting y equal to 0 and solving for x. Okay, so what that means, that gives us, so minus f of x0 equals f prime of x0 times x minus x0. And that leads to minus f of x0 equals f prime of x0 x minus f prime of x0 x0. And then when we solve for x, that's going to give us that I'm going to get f prime of x0 x0 minus f of x0 equals f prime of x0 x. And lastly, isolating x, I get that x0 minus f of x0 divided by f prime of x0 is equal to x. So this is going to be my new value. This is going to be my new x1 value. Okay, right? Remember, I start with x0. I draw this tangent line. I have an equation for the tangent line because I know its derivative is, I know the slope is the derivative, and I know a point on it. And I want to know, when does this cross the x-axis? So to do that, I take the equation of the line. Crossing the x-axis means y equals 0, and I solve for x there. So it turns out that we have this formula. X, our new x, is going to be x0 minus f of x0 divided by f prime of x0. Okay, so I have that formula here on the next page. So the method on this, so if we want to find a solution to f of x equals 0, and we start with a guess x0, then the method on the previous slide says that our next guess should be, we'll call it x1. It's we take our original guess, and then we subtract off f of x0 divided by f prime of x0. And then the point is, once we have one guess, we can just keep repeating the procedure. So our next guess is going to be x1 minus f of x1 divided by f prime of x1. We could call that guess x2. And then we can do a new guess, which we could call x3, which is going to be x2 minus f of x2 divided by f prime of x2. At each step, we're just using the same procedure of drawing this tangent line and seeing where it hits the x-axis. And that's going to be good enough to just get us closer and closer approximations to the answer. And in fact, if you have your calculator solve an equation, if you have a graphing calculator that has a solver that tries to solve an equation, this is the basis for what it is doing under the hood. It's basically doing Newton's method to try to solve these equations. It's not using algebra techniques from because you could write down some equation that's very hard to solve with algebraic techniques. Something like e to the x minus x equals 5. You're not going to be able to solve that with standard techniques, but you can get a good enough approximation to a solution by using Newton's method. Okay? So your calculator is doing this procedure when it's trying to solve an equation using Newton's method. Okay? So let's see, what Newton's method then gives when we're trying to do certain things. Okay? So let's do an example. So let's again try to compute the square root of 101, but we're going to do it using Newton's method instead. So one way of thinking about the square root of 101 is that it's a solution to x squared minus 101 equals 0. Right? That's one way of thinking about it. So we have x squared minus 101 equals 0. Okay? And, well, I don't know, a solution is 101. I don't know, but let's take our first guess, x0 equals 10. That should be pretty close to a solution because 10 squared is pretty close to 101. So with Newton's method, I'll just recall the formula. Another way of writing it in general is that x n plus 1, your n plus first guess, is equal to your nth guess minus f of xn divided by the derivative of xn. This is what we have. So x1 in our case. So in this case, f of x is x squared minus 101, and f prime of x is just 2x. Right, so this is pretty easy. So x1 is going to be x0 minus f of x0 divided by f prime of x0. X0 is 10, so that's going to be 10 minus, well, f of x is going to be 10 squared minus 101 divided by 2 times 10. Right, this here is f of x0, and this here is f prime of x0. And this here is just x0. So if we simplify this, we get 10 minus, then up here we have a negative 1 on the top because that's 100 minus 101, and divided by 20. And this is the same thing as 10 plus 1 over 20. And this is exactly what we get by the tangent line approximation. So in fact, with this question, the first thing that you get is going to be the tangent line approximation. Okay, so this x1 is 10.05 to start with. So we're going to do one more step of this. Okay, so the first step, we applied Newton's method, and we just get 10.05. All right, let's apply the second step. So x2 is going to be x1 minus f of x1 divided by f prime of x1. What's that going to be equal to? Well, x1 is 10.05, and now we're going to subtract 10.05 squared minus 101. And then we'll divide that by 2 times 10.05. So this calculation gets to be a little bit harder. So this is 10.05 minus, well, it turns out what is 10.05 squared? You can do it by hand if you need to, but just to save time, I'll do it on the calculator. This is 101.0025 minus 101, and then divided by 2 times 10.05, which is 20.1. Right? So let's keep simplifying this. That's 10.05 minus, what is that? So 101.0025 minus 101 is 0.0025 divided by 20.1. Okay, or another way of saying this is that's 10.05 minus, well, 0.0025 is actually 1 over 400. So 1 over 400 divided by 20.1, which is equal to 10.05 minus 1 divided by 400 times 20.1. And this is 10.05 minus 1 over, well, 400 times 20.1 is actually going to be, well, what is that? That's 40 times 201, so that's going to be 8,040. That's what we get here. Okay. So now you actually do have to put this into a calculator. You probably can't do 1010.05 minus 1 over 8,040 by hand. So let me just do that. So this comes out to be 10.049876. And amazingly, this is correct for the square root of 101 up to all 7 decimal places. So this is correct to 7 decimal places. Okay, so even just using one step of Newton's method, we get 2 decimal places. It's kind of like the tangent line approximation. And now if we do a second step, here we're just plugging in x1 equals, right here, here we have, this is x1, this is f of x1, and this is f prime of x1. We plug that in, and you end up getting this amazing answer that's correct, that approximates the square root of 101 correctly up to 7 decimal places. Okay, so from this, even if you needed a calculator to do 1 over 8,040, this is telling you that up to here, you didn't need a calculator, right? So square root of 101 is extremely close to 10.05 minus 1 divided by 8,040. Okay? So these two steps of Newton's method gives you the square root of 101 up to 7 decimal places. So that's pretty amazing. And if you did another iteration, you'd get like 20 decimal places correctly. And so when your calculator is solving square root of 101, it's just doing this. And once, if it's solving x squared minus 101 equals 0, it just does this. And once it does 2 or 3 iterations of Newton's method, it has enough decimal places to display on its screen. So that's all that it needs to do. Okay. So the Newton's method, it's pretty simple, right? It's a pretty simple formula. You start with a guess, and to get each subsequent guess, you subtract f of your guess divided by f prime of your guess. And you just keep doing that over and over again. Going back to our formulas here, x0 minus f of x0 divided by f prime of x0, that gets you your next guess. And then x2 gives you x1 minus this, and then x3 gives you x2 minus this, and your guesses just keep getting better and better. Okay, and it's a very simple method. And the only drawback to Newton's method is that if your first guess is bad, then you could run into trouble. Like if your first guess was something that had derivative equal to 0, then of course the method breaks down because you're dividing by 0, which you can't do that. But generally, you will avoid this as long as your first guess is close enough to the actual answer. So as long as you have some idea what's the actual answer, well, x squared minus 101 equals 0, we want to solve for that. Well, I know that the real answer is root 101, but I know that 10's at least pretty close. Then I can start my method with 10, and this gives you a real by hand method to compute the square root of 101 to a lot of decimal places.
Hello?
Yes, question. Rash?
Yeah, all right. The 8,040.
Yeah.
I really don't know, get it, because if you divide 0.0025 divided by 20.1, it gives us 0.00124, and so on, right?
Yeah, that's fine. But use the calculator for that, right?
So I would get the 8,040. That's where they
Oh, I was just pushing this as far as I could without using a calculator. So 0.0025 is 1 divided by 400, right? Because 0.25 is 1/4. So if you throw in 2 extra zeros, that's 1 divided by 400.
Okay.
Right? So I wrote this as 1 divided by 400. But if you do 1 divided by 400 divided by 20.1, that's just the same as 1 divided by, you can just put the 400 in the denominator. So it's 400 times 20.1.
I understand.
Right, and then 400 times 20.1 is 8,040.
I understand. Thank you.
Okay, you're welcome. Other questions? Okay, so yeah, Newton's method is pretty amazing. So there will be an example also on the homework. To do Newton's method, let's say I gave you this equation, x to the 5th minus x minus 1 equals 0. So approximating a root means a solution to this equation equals 0. Well, this is not something that you can factor. You're not going to be able to do this using just explicit algebra. But what I can say is that if you start with x0 equals 1 and you do Newton's method 2 steps, you're going to get very, very close to an actual solution to this equation. Okay, so you will be able to solve this to a good number of decimal places without having to use any kind of like function solver or anything like that. At worst, you just have to use like a calculator to do some division. Okay, so this is going to be problem 2 on the homework. So use Newton's method. Start with a guess of x0 equals 1. That's maybe kind of close to a solution. You plug it in, you get minus 1. Maybe that's kind of close to 0. And then after 2 steps, you're going to see that you get very close to an actual root here. Okay, so that's homework exercise number 2. Okay, so we have 25 minutes, so I think we can do one more topic. So this is everybody's favorite topic, which is L'Hopital's rule, which is a good way of evaluating limits. So this is actually done in the book. It's kind of in a weird sequence. This is not done until section 6.6. Oh, no, wait, no, 5.8. Yeah, so this is done in section 5.8 of the book. We're only going to do for now the basic form of L'Hopital's rule. Okay, so let's say you want to evaluate a limit that's in the form of a fraction. So f of x divided by g of x, limit as h approaches a of f of x divided by g of x. And this a is very general. This works for limits to infinity. It works for one-sided limits. It works for any kind of limit. So, so now suppose that if you take the limit, so one thing you can try to do is you just plug them in. If you just plug in the value a on the top and the bottom and you get a sensible answer, then you win. That's your limit, right? As long as, I guess I should be assume that f and g are differentiable at a. Okay. But now imagine that you get something like 0 over 0 when you plug in x equals a, or something like infinity over infinity. So if you think way back to our limits unit, in order to evaluate these limits that came out to 0 over 0 or infinity over infinity, these things were indeterminate. And so you needed some kind of special algebra tricks to figure out the limits. You needed to multiply by the conjugates, or you needed to cancel a factor, or you needed to, divide the numerator and the denominator by something. You needed all these tricks to do these limits. L'Hopital's rule says all that you need to do is to do a limit like this, take the derivative of the numerator and take the derivative of the denominator and evaluate your new limit. And if that works, then that is the limit that you started with. Okay, so the limit as x approaches a of f of x over g of x is just the same as the limit as x approaches a of f prime of x over g prime of x, as long as this latter limit exists. Okay, so what's nice about L'Hopital's rule is it's usually a very, very easy way to evaluate limits. Okay, so an example, let's say we have I've got two examples here. So we have the limit as x approaches 0 of sine of x over x. And here we have the limit as x approaches infinity of 6x squared plus 7 divided by 2x squared minus 5x plus 8. Okay, well, remember, when we actually evaluated the limit of sine of x over x, we had to draw a circle and do all this crazy, squeeze lemma, and it was not an easy limit to evaluate. And we needed to do it in order to derive that the derivative of sine x was cosine x. So what we're doing here is a little bit circular. But what do I do here? Well, the limit as x approaches 0 of sine of x. Well, if I punch in x equals 0, well, I get sine of 0 over 0, which is 0 over 0. This is indeterminate. So use L'Hopital's rule. And so that tells me that the limit as x approaches 0 of sine of x over x is the same as the limit as x approaches 0 of, I take the derivative of the numerator, that's cosine of x, and I take the derivative of the denominator, that's just 1. And note that I'm really taking the derivative of the numerator and the denominator separately. I'm not doing the quotient rule. The quotient rule, remember, was complicated. It was derivative of the top times the derivative of the bottom minus derivative of the bottom times the top over the bottom squared, whatever. It was complicated. But here, it's just simple. It's derivative of the top, derivative of the bottom. That's L'Hopital's rule. And you take that same limit, and now, well, the limit as x approaches 0 of cosine of x over 1. This is just cosine of 0 over 1, which is 1 over 1, which is 1, right? So this limit is just equal to 1. Okay, by
yes, sir.
Yes,
sir.
Prince.
Yeah, so you just take the limit of sine over x, sine of x over x, and it's because we found the inverse of sine, so I get cos x over 1.
Not
Is
inverse, derivative.
We take the derivative.
Derivative, yeah. So sine goes to cosine, and x goes to 1. This is always by taking d dx, taking the derivative. Okay. Right, so this is just going back to here what it is. You start with f over g, you can replace it with f prime over g prime. That's the derivatives here. That's how the L'Hopital's rule works.
Yeah, so that means the derivative of sine is cosine. That what you mean?
Well, I mean, it's kind of circular. We're saying that if you already know that the derivative of sine is cosine, then you can evaluate this limit to get 1. Now, that's kind of not really allowed because we had to evaluate this limit in order to know that the derivative of sine was cosine. That was part of the proof. So we're kind of doing circular reasoning here. But so you should think of this maybe as a verification. We know that the derivative of sine is cosine, and we can use that to verify that the limit as x approaches 0 of sine of x over x is equal to 1. Once we know the derivative of sine is cosine, then we can evaluate this limit. And likewise, if we can evaluate this limit, you can show that the derivative of sine is cosine, although that was a fairly complicated proof. Does that answer
Okay.
your question?
Yeah, thank you. Thank you.
Okay, you're welcome. Other questions on this particular example? We'll do the other example afterward. Okay. All right, let's do the other example. So limit as x goes to infinity of this. Well, normally we would again just get an indeterminate form because this would just turn out to be infinity over infinity, which is indeterminate, right? As x goes to infinity, the numerator goes to infinity, and the denominator also goes to infinity, right? So again, we're going to use L'Hopital's rule. So we take the derivative of the top and the bottom. So the limit as x approaches infinity of 6x squared plus 7 over 2x squared minus 5x plus 8. Well, this is equal to the limit as x approaches infinity of, so the derivative of the numerator is 12x, right, plus 0. And the derivative of the denominator is, well, the 2x squared becomes 4x, and the 5x becomes minus 5, right? 12x over 4x minus 5. And you could say, well, what happens here? This still gives you an indeterminate form. It's still infinity over infinity, right? Because if I go to infinity, 12x goes to infinity, and 4x minus 5 also goes to infinity. So it's still
Yeah.
an indeterminate form. Yeah, Prince?
Yeah, but we can just state the derivative of the 12x and the 4x to give a number.
Exactly. So you just use
I think
L'Hopital's
it
rule
will be
again.
3.
Yeah, exactly. So Prince is right. You just use L'Hopital's rule again. And now this gives you that the limit as x approaches infinity of 12x over 4x minus 5 is equal to the limit as x approaches infinity of 12 over 4. And that's a constant, so it doesn't matter that x is going to infinity. So this is clearly 3. And that's your answer. And now, if you remember these types of limits when we did them, you know that you can get the answer by looking at just the leading terms. So in this case, you would just ignore everything else and just look at 6 divided by 2. That would give you 3. That's the correct limit. So L'Hopital's rule is giving you another way to solve the problem. And it gives you the same answer because it has to give you the same answer. So this 3 is something here that you could get by just comparing the leading coefficients. But L'Hopital's rule, lets you do it also. Okay, so it's sometimes like a nice, quick way to evaluate limits of fractions, where if you just try to like do the limit of the numerator and denominator separately, you get an indeterminate form. L'Hopital's rule will sometimes help you get a form that's better. All right, was there a question?
Yellow.
Yes, Rash.
So if you use the infinitive by saying, dividing the higher power by saying 6s squared divided by s squared plus 7 divided by s squared, everything, both to the numerator and denominator.
Right, that was the original way we had before L'Hopital's rule. That's how we did it before. When we did these limits in the fall, that's how we did them. Other questions? Okay. Okay, so I think that's enough for today. We did really 3 new topics, these tangent line approximations and Newton's method and L'Hopital's rule. So I think that's enough topics for today. And and also all of this reviewing of related rates and the chain rule. Okay, so let's just leave with the homework. So we have a homework exercise for each of these techniques. So the first one is use a tangent line approximation to approximate 1 divided by 4.002 without using a calculator. So we already gave you the hint, is that you're going to use this function 1 over x, and you're going to try, you know what that's equal to when you plug in 4, and you want to know what is it equal to when you punch in 4.002. So you'll use the tangent line approximation formula there. Number 2, use Newton's method with 2 steps to approximate a root of x to the 5th minus x minus 1, where you start with an initial guess of x0 equals 1. And number 3, try to, and this is a limit that you probably couldn't do before, but becomes much easier with L'Hopital's rule, is evaluate the limit as x goes to 0 of sine of 4x divided by tangent of 5x using L'Hopital's rule. And my hint here, or hint/warning, is that when you take the derivatives here, you will need to use the chain rule. Okay, and that's because sine of 4x is a composite function, right? You're doing 4x and then you're doing sine. So to use L'Hopital's rule, you have to take the derivative of the top and the derivative of the bottom, and you'll need to use the chain rule in order to do that. Okay? So these are the homework exercises for next week. So 1 on each of the 3 topics that we discussed today. And next week, we will have class next week. We shouldn't have any days off for a while. And so next week, we're going to discuss the beginnings of what's called integral calculus. We're not going to do very much integral calculus, but I do want to at least do the very basic physics applications. So we're going to talk about antiderivatives, which is kind of reversing the process of taking derivatives, and what that has to do with motion, with the relations between speed and velocity, between position and velocity and acceleration. Okay, so that's what we're going to do next week. Okay, any questions?
Yeah, Andrew.
Yes, AB.
Andrew.
Yeah. AB.
Thank you very much for the class. Yeah, thank you very much for the class today.
All right, you're welcome.
That next week on the 20th, everybody will be there again. Thank you very much. Let us continue. But we'll still get back to you. After the month, we'll get back to you to tell you when we'll be able to get the post certificate.
Okay. Yes, please. Yeah, at this point, I can't really do anything. The certificates are in Liberia, so I can't help, unfortunately, now.
Yeah. I know that. Yeah.
Okay,
thank you.
All right. You're welcome. All right, I'm going to stop the recording. Where is this?